In this second part, what I want to tell you about is the great breakthrough, which was the classification of the finite simple groups. Let me start with some simple examples. Z sub p, the cyclic group of prime order p. How do I describe this? Well, one way is to think of it as the group of rotational symmetries of a regular p-gon. Here is a regular 5-gon, regular pentagon, and what I'm talking about is the group of rotational symmetries. I can leave the pentagon alone. I can rotate it through 1/5 of a turn, 2/5 of a turn, 3/5, or 4/5. I've got 5 operations I can do. If you like, if we think of one of those operations, the rotation through 2 pi by 5, as being an operation, let me call it A, then the operations are A squared, A cubed, A to the 4th, and A to the 5th, which is the identity. We're right back where we started. That is typical of a cyclic group. In fact, the additive group of the integers modulo p is a cyclic group of order p. Cyclic groups of order p have no non-trivial subgroups at all. The only subgroups are the identity subgroup and the whole group. And a fortiori, these are the only normal subgroups, and so certainly these groups are simple. Perhaps more famous simple groups are the so-called alternating groups. Take a number n greater than or equal to 5. Take the set 1, 2 up to n of integers, the first n integers. The alternating group of degree n is the collection of all even permutations of 1, 2 up to n. A permutation is simply a reorganization, the operation of permuting the numbers 1, 2 up to n. Evenness is a technical condition that a permutation may or may not have. Every permutation can be obtained by a sequence of transposing 2 of the numbers 1, 2 up to n. If we can get the permutation as a product of an even number of transpositions, then that permutation is even. If not, not. We find that half of the permutations of 1 up to n are even permutations, the other half are odd. If we concentrate on the even permutations, we have the alternating group of degree n. If n is at least 5, then that is a simple group. So here we have 3 infinite families of simple groups. There are more than these that are known. I'd like to give you some indication of what they are. The complete list is far too complicated for a lecture of this kind. Nevertheless, I hope to give you a sort of survey of the known simple groups. First of all, there are a number of infinite families. In fact, there are 18 infinite families. There are the ones we've just seen, the cyclic groups of prime order, 2, 3, 5, 7, 11, 13, and so on. 65,537 comes in there somewhere. The alternating groups of degree n, when n is at least 5. These are quite big groups. Even the smallest of them, the alternating group of degree 5, has 60 members. Too big for it to be sensible for you to think of writing down a Cayley table. The alternating group of degree 6 has 360 members, and so on. The alternating group of degree n has n factorial divided by 2 elements. Quite a lot of elements. Then there are a number of families which nowadays are known by names like this: a n of q, b n of q, There's Cn of q, Dn of q, E6, E7, E8, G2, and so on. There are 6 two-parameter families, A sub n of q, B sub n of q, and so on. Then there are 10 one-parameter families, like E8 of q, there's E7 of q, G2 of q, 2E6 of q, and so on. 16 families of these so-called groups of Lie type in all. Those families, some of them are called classical groups, some of them exceptional groups, some of them twisted groups. Well, those are the infinite families of known simple groups. There are also another 26 so-called sporadic groups. I can't list them all for you. They get too complicated. The first ones to be discovered in 1861 were the so-called Mathieu groups, M11, M12, M22, 23, 24. The subscript there indicates that these are subgroups of corresponding alternating groups. M11 is a subgroup of the alternating group of degree 11. It's a group of permutations of 11 objects. M12, a group of permutations of 12 objects, and so on. M24 is a group of permutations of 24 objects. And for a very long time, these were the only sporadic groups known. Until in 1965, Zvonimir Janko, then in Australia, announced the discovery of a new simple group, now known as J1, Janko's first group. He's got 4 groups named after him. Quite a small group by modern standards. Its order is 175,560. And that was the first of 19 other, no, not 19, 21 groups that were discovered between 1965 and 1981. There are 19 groups I'm not telling you about. And finally, the Fisher-Grice monster, whose existence was indicated by Fisher and Grice independently in 1973. Bert Fisher working in Bielefeld in Germany, Bob Grice working in Michigan, in Ann Arbor in Michigan. In all, as I've said, 26 sporadic groups that do not fit into those 17 or 18 infinite families. Just to give you some idea of the size of these things, the smallest of the sporadic groups is the Mathieu group M11. Its order in factorized form, which is the way it comes out in group theory, is 2 to the 4th times 3 squared times 5 times 11, which is 7,920. It's very small by modern standards, but it's far too big for this group to be described by a Cayley table. The Fisher-Grice monster, its order is 2 to the 46 times 3 to the 20 times 5 to the 9, 7 to the 6, 11 squared, 13 cubed, 17, 19, 23, 29, 31, 41, 47, 59, 71. Multiply all those together, and what you get is about 8 times 10 to the 53. It's an enormous group. Can't be described by a Cayley table, but it's described as the automorphism group, the symmetry group of a certain structure. In this particular case, it's an algebraic structure, which is why I've called it A. It's in fact an algebra, a vector space with a multiplication upon it, and the dimension of this space is 196,884. So we come to the breakthrough. And I'd like to describe the breakthrough in this way. It is the theorem that any finite simple group is one of those in the list of known simple groups. And when I say it is one of those in the list of known simple groups that I've described, the 18 infinite families and the 26 sporadic groups. When I say it is, what do I mean? I mean it's, in technical terms, isomorphic to one of those groups. That is to say, you can relabel the members of this finite simple group so that the multiplication is the same as in one of those standard groups. It's a tremendous theorem. The proof was perhaps completed in about 1980. I believe that all the ideas were there and most of the details were there. The whole project to prove this theorem had been orchestrated by Daniel Gorenstein in the 1960s and 70s, and the final parts of the proof, main parts of the proof, were produced by Michael Aschbacher, but many, many other people contributed. There was a correction, which I'll tell you about a little later, that has just been announced. To try to give you some idea of the scale of this achievement, let me go through a very brief history of the theory of simple groups. Évariste Galois, in a letter that he wrote on the night before he went out to be shot in a duel at the end of May 1832, gave the definition of a simple group. There wasn't really any group theory around at that time. He was way ahead of his time, a lad of 20, shot in a duel. 1870, nearly 40 years later, Camille Jordan wrote the Traité, a 600-page book, essentially a commentary on the work that the young Galois had written before he died in 1832. And in that Traité, Jordan focuses on the importance of the notion of simplicity. And between 1870 and 1901, gradually the list of known groups grew. The 5 sporadic Mathieu groups were discovered. Various of the other classical groups, orthogonal groups, unitary groups were discovered and listed. From 1892 to 1904, mathematicians like Otto Hilde in Germany, Georg Frobenius in Germany, William Burnside, who was then professor at Royal Naval College in Greenwich, they were producing classification theorems. For example, Burnside proved in 1904 that a simple group must have either prime order or at least 3 different primes dividing its order. Then there was a bit of a pause, but in 1956, Claude Chevalier showed how the so-called continuous groups, the Lie groups that were important in physics, had analogues for finite groups. And shortly after that, the system that he proposed was modified to include the so-called twisted types. And by 1962, that list of 16 families of groups of Lie type that I gave you before was complete. In 1963 came the first really great breakthrough when Walter Feit and John Thompson published a proof of what's now known as the Feit-Thompson theorem, which tells us that simple groups of odd order, simple groups with an odd number of elements, are just those that have a prime number of elements, the cyclic groups of prime order. Between 1960 and 1980, a wealth of new classification techniques came in. Between 1965 and 1980, 21 new sporadic groups were discovered. And it all came together. In 1980, the classification essentially completed. What about the present and the future. The first great task that has occupied Daniel Gorenstein and various of his colleagues in Rutgers University and other parts of the world is the project called Revisionism, Reworking the Proof. In its form in 1980, it was well over 10,000 pages long, an unbelievably long proof of one theorem. And of course, in 10,000 pages, you must expect there to be gaps, errors, slips. Worse than that, it was discovered about 4 years ago that one piece of the classification, the so-called classification of quasi-thin groups, which it had been believed had been completed, may have been completed, but only half of that particular piece of the classification was published. Well, this year it's been announced that Aschbacher took up the challenge and has completed the classification of the quasi-thin groups. Even so, I believe there must be further gaps. But I also believe that we have the techniques, that any gap really should be thought of as a slip, that we can fill it in. So I believe that the classification of the simple groups is complete. But of course, what's needed is to civilize the proof, bring it down to a reasonable size so that we can all understand it and believe it. But already we're exploiting the theorem. We're believing that the classification of the simple groups is complete, even if it isn't, of course, on the hypothesis that there are no new simple groups beyond those that we know. We can solve many of the old problems of group theory, of number theory, and many new areas are opening up. But these are too technical. They'll have to be the subject of a popular lecture at some time in the future.